Welcome to Hot Chips 20. Session 4, Supercomputing.
After every talk, remember that between you and dinner is just your number of questions. And so with that, I'd like to really introduce the session. It is on supercomputing. Some people call it big iron, as in big systems. The previous session was all about small chips, tiny chips. This is not necessarily about big chips over here. It's about big systems. But interestingly enough over here, as you will see in the next two presentations, it's all about efficiency as well. So we have one talk on the latest version of the cell processor from IBM, and we have an interesting talk about a molecular dynamics focused custom ASIC from D.E. Shaw Research. And with that, I'd like to hand it over to Brian Flachs. He is the main architect of the SPE. That's the synergistic processing element that does all the heavy-duty number lifting in the cell. He actually received his undergrad degree from New Mexico State, and he was for graduate work he was right here at Stanford, so he likes to come back to the area, and we managed to get him over here to give us an update on the latest in the cell architecture, in particular the SPE. Thanks, Brian.
Can you hear me? Okay, good. So I could have titled this talk From the Living Room to the Football Field. But I'm a little too straight up for that sort of thing. A lot of people worked on our project. This is a small number of them, as you can tell. Everything that we do is a partnership. So what are the important attributes for a supercomputing node? And what sort of words do you have to tell people when you're trying to put in a bid for one of these things? Well, of course, the first thing that you have to start talking about is double precision flop rate, and there's a significant number of applications that can actually be coded up almost without concern for the memory system that hit whatever peak flop rate your machine is capable of. So you have to talk about IEEE compliant double precision flops. Another important parameter is memory bandwidth. Again, there's a significant number of supercomputing applications that run at a rate determined by how many bytes you can move to and from memory. And then we get a little bit more subtle. So memory per compute node regulates some algorithms, what sort of blocking you have to do to get to the peak double precision rate. It also can control what the data set size is and how many nodes you have to do the computation. Communication and I/O is exceedingly important when you start talking about taking, multiple tens of thousands of processors and trying to do a single computation on them. And then there's when you're trying to build the machine in the first place, not everything that you get is perfect, and so you have to sort through all of the bad hardware and whatnot. And so it's very important to be able to isolate failed components and get them out of your machine before it becomes stable finally. And most of the big machines operate on the notion of taking checkpoints every once in a while. So the every once in a while is governed by how long your machine is expected to be up. So the longer the uptime, the fewer checkpoints, so the more useful computation you can get out of your machine. So how does cell stack up? And kind of a refresher about what it is. This is a die photo of the original 90 nanometer cell chip, and you can see that there's a PowerPC processor and an L2 on this side, and an array of 8 synergistic processing units there. So the synergistic processing element, I'll tend to switch between SPU, SPE, whatever, but it's a fairly efficient design. About 1/3 of it is the 256 kilobyte local store. About 1/3 of it is data flow, and about 1/3 of it is a DMA engine. So this thing can provide lots of flops on the data flow here, but it's very single precision centric. We did include double precision operations in the instruction set, but the unit that we have is small and not particularly suitable. So we took a lot of hits for about 1.8 double precision gigaflops. So that's an area where we don't match up with what it is we need to sell to a big HPC customer. What's really special about the SPE is this DMA engine business. So using the DMA engine, a lot of supercomputing applications can efficiently drive memory bandwidth and become, when written in this way, exhibit good latency tolerance. And in this way, we can move a fair amount of code. The general purpose application is a slightly different case, but a lot of the vector codes decompose easily into this model. So that's pretty nice. And of course, for its generation, the Cell BE provided a lot of main memory bandwidth. And that was one of the things that we have to go talk to people about, why it's great. But the downside is that the gaming memory system allows us only to build out about 1 to 2 gigabytes of memory per cell chip, and it's all soldered down, and it's so there's no notion of expandability or anything like that. So the net of this is that for supercomputing, things are very promising, but slightly unacceptable. And so we need to do some work on improving the double precision flop rate and the memory capacity issues before we have a compelling supercomputing product. So of course, the first thing to do is go see what you can do about double precision flop rate. And so we got out our surgery gloves and we cut out the old double precision unit. And the interesting thing about the old double precision unit is we were severely constrained by power and area budgets when we were building it. So the unit itself has a 13 cycle latency, which wasn't, was too long for the control unit. We couldn't sequence instructions with pipelines that deep. So we just threw up our hands, installed for 6 cycles, and made the effective pipeline about 7 deep. It wasn't IEEE compliant, and although we have a two-way SIMD architecture, we had to double pump this unit to get both results. So we tear out that, and we designed some new unit, and we put 2 of them up on top of the chip. And so in this implementation, we were not nearly area constrained and power constrained as we were, so we can fix a number of the problems. So the second thing is we improved the IEEE compliance, and this was required by the folks we were doing business with. They wanted to be able to pass paranoia. And so we had to work on the D norms and then NADA numbers so that they adhere to the IEEE standard. And we also put 5 new double precision compare instructions into the architecture. So the way that compilers were emitting code wasn't particularly IEEE compliant because it was too slow to do so. So the new double precision compare instructions help that out. The next thing we have was important to get the flop rate up is to pipeline the double precision unit. So we spent our area and our power to get the unit latency down to 9 cycles, and then we stretched the instruction sequencing logic to cover the 9 cycle latency. And the result of all that is that double precision now dual issues, whereas before it sort of locked up the pipeline for a while, and we can get a total of about 102 gigaflops of double precision floating point out of an SPE. And so that's a factor of, 7 or 8 or something like that. Or 102 gigaflops is wrong. That's per PE chip. But anyways. So I put up some reference slides here to show you how things are pipelined on Cell BE and how they're pipelined on PowerXCell 8i. So you can see that the issue rules are a big performance limiter. And if you're involved in a chip design, the best thing to do is contain your latency, and most of your problems will go away. So how did we do this miracle of 13 cycles to 9 cycles? So as you progress in technology levels, the transistors are sort of getting faster than the wires are in a normalized sense. So one thing that you do is you put more transistors per cycle, and then you have to work on trying to contain your wire-dominated paths. So to do that, we moved from, if you remember on the previous slide, we had sort of a single stick of double precision unit going straight up. Now we have this two-column floor plan that where the result goes in and the inputs go in and the result comes out sort of the same place. And this organization of blocks cuts a number of the long wire paths within the unit by significant fractions. We also spend our area and power budget to include about 10% of low threshold transistors on some of the critical paths to make some of those fit underneath the wire-dominated paths. And we also took an opportunity to build higher fan-in logic structures to beat, for example, the normalizer mux that used to account for 2 cycles into 1. So the final thing that we had to do to make it all fit was do some cycle stealing. And so if we do all of those things, we can get 13 down to 9. So that was sort of one half of fixing one half of what was wrong with cell BE. The other thing that was wrong with it was that we didn't have enough memory capacity per cell chip. So we wanted to get to a point where we could have a variable memory capacity by installing DIMMs. So that means leaving the soldered down realm. And so we chose DDR2 SRAM, and PowerXCell 8i can run up to 800 megabits per second. And we can get between 8 and 16 gigabytes of memory per cell BE, depending on whether it's dual rank or not. But we maintained the organization to be sort of mirroring the organization that we had on the original cell BE. So we still have 8 banks of memory with 2 channels apiece, so that all of the code optimizations that had been done on the regular cell would carry over onto PowerXCell. So we tried to maintain as much compatibility as we could. So supporting DDR2, we have our memory controller has 64 commands in its queue, and it does silent reordering to try to minimize the number of times it switches pages within a DRAM and tries to spread the accesses out on the multiple banks. And it tries to minimize the number of times it switches the bus from doing read commands to write commands. All in all, since we have all of the SIMs are directly attached to the cell BE, we have an increased pin count here up to 540 pins dedicated to the DDR2 interface. And so we continue to have about 25 gigabytes per second of memory bandwidth due to this number of pins. And so that number of pins, you'll see a little bit later, we had to grow our package, and we had to add a new supply, and we needed a whole bunch more decoupling capacitance to make this all work. So there's our die photo. So sort of in this rectangle here, you can see the original cell BE. And then on this side over here, where this is the new DDR2 interface. And you can see that there's a lot of I/O there. This is the more or less the original memory controller area that we've made some modifications to, but not too many. And then you can see, roughly speaking, the SPE bounding box is here, and right there is an EDP module, which I've shown there. So in some senses, given the DDR2 interface and the chip growth that was required to bolt that on, the enhanced double precision is slipped in for free. So building fixing up some of the immediate deficiencies in cell BE wouldn't have been enough to build a large-scale supercomputer had we not done an initial design that struck a fine balance between a consumer electronics device and a server device. So in particular, there's a fair amount of of logic in the chip that deals with soft errors and hard errors and counting them and make it easy to identify system failures and where they are and what components need to be replaced. So this became and it also, reading these systems also allow you to know that failures have occurred in the chip or in the system in general, and tell you when to get your previous checkpoint and install it, so you can rerun the computation. So the soft errors I talked about occur randomly, and there's nothing really wrong with your computer hardware, with your hardware itself. These errors can afflict every piece of your machine. And so they can crash it, they can make your answer turn out wrong, whatever they want to do. So what we'd like to do is maximize the number of times that we can recover in a graceful fashion, and with as little disturbance to the overall system as we can figure out how to do. So SRAM and DRAM are the significant sources of errors in our systems. On the cell chip and the PowerXCell 8i, there's 3 categories of SRAM. By and large, those that hold the only copy of a particular piece of data are protected by ECC, so this means that a single bit flip won't bring down the machine. We can recover from that and restore the correct values. But double bit errors, of course, will cause a check stop. There are those arrays that hold only copies of data that can be found elsewhere. So these arrays are typically covered by parity, so a bit flip there will cause the machine to realize that there has been an error, flush out the array and reload it from the backing store. So the SPU local store and the PPL2 are the real copies of data, and we don't have anything else, so we have to protect those by ECC, whereas the L1 caches are, well, the I cache doesn't write, but the D cache is a write-through, so we can protect that with parity only. And then there's a few others on the chip that are just not recoverable, and so we had hoped when we designed it that they were either too small to matter, or when we looked into the cost of building protection circuits for them, we felt like it was damaging to the notion that we'd be a consumer electronics device. So that ends up with sort of an error breakdown as to, why we expect PowerXCell 8i to fail. And so what you can see is that double bit errors on the ECC protected arrays account for only about 3% of the expected failures to PowerXCell. Whereas these 4 arrays inside the memory controller, relatively small arrays, turn out to dominate our failure rate. So that's an area where next time around we're probably going to have to look at what we can do about those arrays to improve our error tolerance. So off-chip data integrity is just as important, if not more important, than the on-chip data integrity. So our memory bus and our I/O buses are both protected in various fashions. So the memory bus, of course, is protected by ECC, and there's an interesting address hash scheme that allows us to know whether or not a particular datum was stored correctly or not. And we have the I/O controller is the packets to and from there are protected by a CRC algorithm. CRC errors are reported and cause the packets to be retransmitted. So that's some of the sources of errors. Of course, there's a few others. So some of them are recoverable and some of them are fatal. There are parity errors, ECC errors, protocol errors, watchdog timers, hang detectors, and a few other things. So all of these errors are detected in their functional units. And then we have an architecture for managing these error detections. So recoverable errors, we'd like to make it user selectable depending on your bring up mode, whether or not the soft error causes a machine stop, or whether or not the machine attempts to continue. Eventually, when you have to triage these errors, so we take these signals in, we count them, we register them, and then software, either software running on the PPE or software running on the system controller on the blade card can interrogate these values and either cause a software recovery method measures or report these things out to the system console where triage of failed components can occur. So the important thing here is that we have enough information to pin down errors to the faulting units, and so we can take direct action there. You saw sort of a variant of this slide with the power awareness talk. And so what I did is I took a cell BE chip, and I normalized 3 other chips to the same technology, and I drew a box around the 8 SPEs, and then I superimposed that same box onto these other general purpose microprocessors. So the thing that this special purposeness of SPE is giving us is that we can fit 8 SPUs into the area of a general purpose processor plus its, well, this is a dual core, so two general purpose processors plus the L2 cache that's thought to be required to make that function efficiently. So we're getting more or less a natural factor of 4 in performance per unit area by including SPEs in our design. Okay, cool. So by the way, by reducing the number of amount of silicon that we have, we get to have fewer chips in our supercomputer, which means that the more or less errors are proportional to chip area. So we have fewer errors. We get more compute per soft error, which means that we, relatively speaking, have to have fewer checkpoints taken, and we end up with more net productivity than you would have expected just at first glance. I have a whole bunch of charts here kind of showing performance comparisons between various x86 systems and cell BE systems. And you can see that the performance advantage ranges between about a factor of 2 and about a factor of 20 if you scan through the charts. This isn't IBM's work here, but what's kind of interesting is the degree to which a floating point processor like SPE seems to be accelerating more or less integer workloads, searching and sorting and whatnot. It's very encouraging from a cell guy's point of view. So we packaged this thing up to build a supercomputer, and so I'll just quickly flash how we did this. So we built a blade card featuring 2 PowerXCell chips and a PCI Express bridge. So we have 2 of those, and the PCI Express is brought out of those cards and onto an interposer card that converts the PCI Express into hypertransport. And then there's a hypertransport bridge onto a Opteron blade. And the Opteron blade has 2 AMD dual cores on it. So this is what one of the PowerXCell blades looks like. Over here, of course, you have the DDR2 memory. Here you have PowerXCell sitting underneath this bank of copper. There's this interesting cutout thing, and this is where the bridge chip is. And then you take 2 of those in the interposer card and the Opteron blade, and so there's flex cable running along the edges here, underneath here. And so you get what we call a tri-blade, even though it really takes up 4 or 1U slots. And then you take those and you start punching them into racks, and we have InfiniBand switches. Here's another picture of a somewhat related chassis. You can see the tri-blade sticking in there. So once you're out to InfiniBand, we have 2 levels of InfiniBand switch. And that allows us to get 278 racks into the system. We could expand it some, I guess. And we picked out the minimum configuration required to achieve a sustained petaflop on LinPack and called that the Roadrunner system. And that ends up at 12,000 PowerXCell chips and 6,000 dual-core Opterons. So that's 17 clusters and 2.35 megawatts of compute. So when you start talking about megawatts of compute, you start understanding that performance and power are just duals of the same thing. So everything that you do to save power gives you more compute in the state of New Mexico or Illinois or wherever you're going to put the thing. And so there's Don Grice walking around a football field full of computer hardware. It's cool. Did I hit it? Cool.
Time for a few questions. They're not shy. They're not going to be shy.
Okay.
Yes. A question or a comment about, said, more compute power per soft error. Not sure I agree with you there. Maybe yes, maybe no. True, the number of whole electron pairs per square millimeter of silicon will be constant, but the devices are getting smaller, they're getting closer together, and the number of your double bit and even triple bit errors is zooming up, depending upon your architecture and your error detection and correction circuitry.
Well, yes and no. So the bad news, of course, is that a single strike has a larger effective radius. That's true. But things are getting thinner, too. So actually, we found that the error rate per unit area is, roughly speaking, constant. As we go, I was making a statement really about if you takes you in a certain technology, if you can get the same function out of 1/4 of the area, then the statement clearly applies. But since you're talking about across technologies, let me just say that our studies show it to be it's increasing some. The error rate per unit area as you go from 130 nanometer to down to 65 is getting worse, but it's not stunningly worse because things are getting thinner in addition to getting smaller.
So the answer is maybe yes, maybe no, but I see you're working with Los Alamos too, so I'll talk to you about that later.
Cool.
I'm Bob Lance, Stanford. So it looks like you've dramatically sort of increased on one side both the compute and also doubled the data size of your core, and at the same time you've massively expanded your memory. Does this put a lot of pressure on your local store and your memory bandwidth?
No, actually, so people think that the size of local store is related to the size of your data set, and that's actually not true. The size of your local store is related to what the latency is between the DMA command issuance and the time that data is retired to the local store, because it's really a register file that's there to really facilitate pipelining. So the latency of the DDR2 system is a little worse, but not a whole lot worse than the XDR system it replaced.
Haven't you also increased the rate in and out of that by increasing your double precision, like by a factor of 8, and also switching from sync?
Okay, so the question is really, what is the correct balance of double precision flops versus byte of memory I/O? And so we have the same I/O that we had before. So one of the arguments that I made while we were designing the processor in the first place was, anyways, we could build a better double precision unit, but the bytes per flop ratio really isn't necessarily that bad the way it is. And that's true for, so this is a workload dependence question. So software systems like LinPack, there's a large variety of different blocking methods available to the engineers that produce that software. And I have yet to see a system that doesn't run at peak on LinPack, on the DGEM portion of LinPack. So what that says is whatever you can build in floating point, you can block it such that the operands fit in the cache and you can get it up. So when at the very beginning of the talk, I told you that there's a great workload dependence. So some people come at you and tell you that they care only about memory bandwidth, and some people come and tell you that they care only about flop rate. And there are applications where I think on average the improved double precision unit will save you on the order of between 30% and a factor of 2 over ignoring DGEM sort of things. Sure.
Anton from Micron. I have 3 simple questions. The first one is that the integer pipeline extended to 9 stages also.
Yes. So actually, how deep the integer pipeline is an interesting question. I don't think that you can really know that fact. So the pipe stages that an add takes, were 2 in the previous design, and they're 2 in this design. So yes, they remain in the forward macro for 2 stages longer before the results are retired to the register file. But I don't think there's any programmer sensitivity to that fact.
Okay, the second question is your pie chart on recoverable errors. Is it from measurement?
No, that actually was from simulations based on test hardware of test structures.
Okay, third question is fault isolation registers and capabilities. Is it new for the PowerXCell, or did it exist in the previous cells?
Yeah, so that's what, as I say, we kind of got lucky because one of our design goals was to spend as little money as possible upgrading the Cell BE to PowerXCell 8i. And so we had already thought that we were going to try to build server machines out of Cell BE processors, and so all of that infrastructure already existed. And in fact, you can buy from IBM a QS21 product that represents a Cell BE as a server product.
Okay, so the answer is yes, right?
Yes.
Thank you.
Brian would love to have dinner with you tonight. So can we hold questions and we'll just send you have dinner with Brian. We have one more presentation to go upstairs and downstairs over here. Apologize, but we have to keep moving, otherwise it's going to get too late. Thank you, Brian. I'd like to introduce Marty Deneroff. He's here from D.E. Shaw Research. Marty perhaps can tell us a little bit more about what D.E. Shaw does and how they might be related to financials or not. Marty got his undergrad degree at MIT. He did his grad work over at Monmouth in New York. He was working in the Bay Area. He was at SGI for a while. He actually headed up the hardware engineering team that built the Challenge and Origin series. And then he jumped over to D.E. Shaw, and he's going to tell us about Anton, specialized ASIC for molecular dynamics. And with that, I'll hand it over to Marty.
Where'd the clicker go? Hello. Is this on?
If you want to try it.
Am I on? Okay, so thank you all for bearing with me. I know I'm standing between you and dinner, which is a dangerous place to be. I'll try and keep this on time as much as possible so we don't all starve. I'm going to talk today about Anton, a specialized ASIC and a specialized computing machine for molecular dynamics simulation. As Ralph mentioned, I work for the D.E. Shaw Research Group. The group was started by David Shaw specifically to do research in molecular dynamics. We're a multidisciplinary team consisting of a mixture of computational chemists, biologists, computer scientists, electrical engineers, and assorted other vagabonds that have come together in Manhattan to build a special machine to perform molecular dynamics. This thing doesn't seem to be. There it goes. Okay, so you may be asking why build a molecular dynamics simulation engine? We'll talk a bit about that. We'll talk a bit about Anton's overall design and how we used Amdahl's law to govern that design. And we'll finish up with a bit about green computing, which is sort of a strange thing to consider when you're talking about something in the supercomputer class, but I think you'll see that it kind of is. So first of all, what is molecular dynamics simulation? Molecular dynamics is a way to simulate and observe the structure of molecules and how they move around and how they interact with other molecules. And this is simulation based on physical properties. We actually have individual models of every atom in the system, and we compute the dynamics of the system based on the forces they exert on each other. If you're talking about a very small molecule like water, that doesn't seem like much, but if you think about a large biological system containing proteins and the surrounding solution that they're in, you're talking about many tens of thousands or hundreds of thousands of atoms, and each atom in the system exerts forces on each other, so you have a huge many-body problem. So why do we care? Mainly, we're interested in the D.E. Shaw Research Group in life sciences research, in particular drug discovery and validation applications. As you may know, right now, drugs are primarily developed by what's largely a trial and error process. You take 10,000 different potential drug chemicals, drop them in 10,000 petri dishes containing the thing you want to attack, and see which ones kill it. Then you go back and take those and see which ones will also kill the patient by dropping them in 10,000 other petri dishes. And eventually, after 10 years of assorted stages of trial and error, the FDI puts something on the market, and then we see what happens. We sort of would like to eventually change that into something more like electrical engineering, where we have a simulation of what's going to go on, and we can predict it accurately. So one way to think of Anton as a CAD tool for drug design. It also has applications in materials science, which would be using similar processes to predict the behavior of materials, particularly metallic and crystalline structures in plastics. So the molecular dynamics computation, I don't really expect anybody to read this. If you're really interested, look at it in your slide booklet. But this is the basic equations we calculate. The main thing to take from this is they're kind of complicated. And the interesting thing about it is that not so much that the equations are complex, but how many times we have to do them. In order to do a molecular dynamics simulation, you need to break the simulation up into time steps on the order of a femtosecond. That's one notch below picoseconds, for those of you who are trying to figure that out. So we can do time steps on the order of a femtosecond. That's 10 to the minus 15th. And annoyingly, most biological processes take around a millisecond to be observable. So that's 10 to the minus 3. So that means about 10 to the 12th time steps to see something that you would like to see. Now, that's really quite problematic, because if you run molecular dynamics software on any supercomputer that exists today, such as Blue Gene or Roadrunner or something like that, running a 1 millisecond simulation will take on the order of a year, actually several years, to complete. And I don't know about you, but I can't wait a year or more for my simulations to get done when I'm designing something. So this doesn't seem terribly useful for drug design. So Anton's goal was to speed this up to get to under a month. To do the same job. While that's still really, really long and more than I would like when designing chips, it's a vast improvement over drug design as it goes on today, which averages about 5 years before you can start clinical trials. Now, we looked at the problem and we determined that the people designing your Blue Genes and your Roadrunners and your Crays and whatever else are not dummies. They're very, very smart people. And we didn't see any way to build a general purpose computer that could go any faster than they're going. But we said, well, what if we throw out the general purpose requirement and say, we're only interested in running this problem. So we're not really building a supercomputer as much as we're building a molecular dynamics appliance. We're building something that can do molecular dynamics and can't do anything else. And we set a goal that we want to get performance greater than 100x what general purpose processors can get. And we studied the problem and determined the best approach was to build an array of identical ASICs that we connect in a 3D torus. And we, as I said, had our multidisciplinary group, including chemists and who actually design the algorithms that are used for the simulation. So we set out to co-design the hardware and the algorithms and the software all in parallel to optimize it for the hardware design, so that we actually made significant changes to standard molecular dynamics algorithms that run on most software simulations in order to better fit the hardware. Now, we did this knowing that the science of molecular dynamics is ever evolving. It's a fairly new science, been around for, depending on how you count, maybe 40 years from the earliest attempts. And there are significant changes happening. In fact, in the last 10 years, there's been huge changes. So there's parts of the problem that probably don't lend themselves real well to building hardwired logic for, because as soon as somebody makes a new discovery, those would be invalidated. But on the other hand, we found that the biggest bulk of the computations that need to be done are the pairwise interactions, the interactions between pairs of particles. And those are consisting of electrostatic interactions that are governed by Maxwell's equations. And we say, that's pretty good. Maxwell's equation has been around for 150 years now or so, and chances are we're good for the life of the machine. So, given that, we took the part that fortuitously was the biggest bulk of the computation and hardwired it completely. So all that part can change is a few parameters, and that gives us some enormous speed up. So we built these chips that have both a general purpose part that can do the parts of the science that are changing, and a hardwired part that doesn't change, that does the Maxwell's equations work. Then we took 512 of these chips and connect them together into a 3D torus of 512 ASICs, where each one connects to its 6 nearest neighbors. And we partition the problem into spatial voxels, so each ASIC is responsible for simulating the atoms that lie within a rectangular prism of space that ASIC represents. Now, each chip contains two major portions called the flexible subsystem, which is programmable, and the high throughput interaction subsystem, which is not. And these two sections interact by communicating over a high-speed ring bus on the chip. And they also interconnect to the 6 high-speed links, which are parallel high-speed channels, each one of which is running at 5 gigabit per second per wire, and has total bandwidth of approximately 12 gigabytes per second per wire per channel. And we also have on the chip a memory controller for DDR2 DRAM. Coincidentally, our DDR2 DRAM channel has exactly the same bandwidth as my colleague from IBM has in the previous talk. And strangely enough, many other things about the chip, if you go through point by point, will also seem quite similar in certain ways. And in fact, the flexible subsystem, which is the programmable part, has quite a few similarities to the cell processor as well. So what makes Anton so fast? First of all, as I said, the high throughput interaction subsystem, which does the particle-particle interactions. The flexible subsystem, which is programmable, but it's still specialized specifically for the types of calculations, which are mostly geometry-based, that molecular dynamics requires. And the communication subsystem, which takes care of being able to rapidly move data between the local node and the neighboring nodes, because each node needs to interact its particles with particles on nodes around it, and that needs to happen at a very high rate of speed. Also, parallelization. We work very hard to make as many parts of the calculation as possible happen in parallel, and we worked our way through addressing bottlenecks as they popped up until all parts balanced as closely as we could possibly get them, which was quite close indeed. And system integration, we spent a great deal of attention making sure that each bottleneck was addressed to have everything work together smoothly. and to avoid any unnecessary communication paths. Now, this is all sounds great, but it's enabled by the fact that we knew what problem we were trying to run. We don't have to support general purpose workload. We know how much bandwidth we're going to need for each step because we know what that step's going to be, and we can actually tailor our hardware to that. So why do we need the general purpose computation at all? So GROMACS MD code, which is the most commonly used molecular dynamics package in use today, it spends about 71% of its time in particle-particle interactions and about 29% of its time doing other things. So by Amdahl's law, if we took all the tasks that could be done on the HTIS and took that time to 0, we would only get a maximum speed up of about 4. Almost everyone else who's ever attempted to accelerate molecular dynamics has concentrated on that part because it's a nice structured calculation, it's easy, and it's very tempting. And you look at it and you say, yeah, we can speed this up arbitrarily, but they all run up against this wall of a factor of 4 and you're done. So we had to go and start delving into parts that no one has accelerated in the past. So we're forced to contend with all sorts of random crufty calculations that are not so easy to accelerate, as well as the ones that are. So the HTIS calculates, as I said, the electrostatic parts of the force. The flexible subsystem calculates the bond forces, which are sort of quantum effects primarily, certain correction forces, which is sort of calculating and canceling out parts of the HTIS calculation that aren't needed in bond situations, and doing a great deal of work on integration and constraints. Constraints being boundary conditions that are used in the simulation. Also, it maintains pressure and temperature control and migrates particles as they move from one chip to another. Here's a functional view of the time step. We have sort of 4 separate threads going on. We have the long range calculation, the range limited calculation, the bond, and the correction. Those are calculating all the forces. And it starts out by having to get the positions of all the particles in the system into all of those. Then we sum up the forces and then apply constraints, integration, pressure and temperature control, and migration, and then start the next time step. So in the HTIS, what we have is an array of parallel pipelines, 32 of them, each one of which can calculate one pairwise interaction every clock, and a control unit that matches up pairs of particles to send into that, and an interesting pipeline reduction unit that sums up all the forces that act on any individual particle, so that what goes into the HTIS is individual particles. Within the HTIS, it manipulates them into pairs, performs the force calculation, and then sums up the forces that apply to each particle, so that what comes out is forces on a per particle basis, not on a per pair basis. This is really critical, because without it, we'd have a completely unmanageable bandwidth requirement. So the pairwise point interaction pipeline starts out at the top with a particle array and a match unit that is used to find pairs of particles that can interact with each other. Only particles within a certain distance of each other interact, and the match units take 8 pairs at once and look for ones that are close enough to want to interact them, and then sends one down to each PPIP each cycle. And there's 32 structures like this going on in parallel on every clock. Here's detail of one PPIM. And as you can see, there's 32 copies of this, and this is just a lot of math hardware. It implements those equations that I showed you earlier. Now, popping back up, this is the flexible subsystem. The flexible subsystem consists of 4 parallel processing units that are identical, each one of which has a tensilica processor core that's used for control a remote access unit, which is essentially a DMA engine that moves streams of data from remote buffers into local buffers, a scratch pad memory that is the local buffer, and 2 geometry calculators or geometry cores, which are SIMD processors that are specifically oriented for doing geometrical calculations, dot products, cross products, etc. So the box in the square is one of these, and then you have 4 of them in parallel just to get enough throughput. They all run the same calculation in general, although there are parts of the computation where they actually separate and are working on different steps. And at the bottom we have a little strange box called a correction pipeline, which is a thing we use to back out parts of the pairwise calculation. That's when 2 particles are bonded, we actually don't want to calculate the non-bonded forces between them. But since the HTIS doesn't know what particles are bonded, it calculates them for all pairs. And then the correction pipeline is used on all particles that are bonded to recalculate those forces and subtract them off. So the remote access unit is a closely coupled DMA engine that offloads communication and supports up to 128 parallel threads for moving data about particles between nodes. The interesting thing about it is that all communication in Anton is not request-reply sort of communication, but a push style of communication. If we want to communicate with a remote node, we don't wait for that node to ask for the data. We know it's going to need it, and we send the message to that node containing the data early on, and it's there waiting when it gets to that step of the calculation. And so we have push synchronization. Again, this is specialization we're able to do because we know the problem we're running. We've also optimized the geometry core's instruction set specifically for performing the type of operations we need to do, and you can look at the details in your handout. There's a little bit more detailed view of the geometry core, and as you see, each one has got 8 lanes of computation and a large register file, and can perform computations on 2 4-element vectors per clock. It's interesting that the way the computation is expressed, many of the parts of it use a 4-space type of calculation, so we have 4-element vectors rather than typical XYZ coordinates you would use for normal 3D calculations. Other things that make us fast is parallelization. As I said, we have 512 ASICs. Each one's an SoC. I'm often wondering whether Anton is more like a cell phone or a supercomputer. The chip we're working with has got all these dedicated functions, each one of which has a software component, a hardware component, and the software is kind of akin to the firmware in a cell phone in some ways, as much as it is akin to a general purpose supercomputer. So across the whole system, we've got 16,000 PPIMs, 4,000 geometry cores, 2,000 tensilica cores, all in 512 ASICs. So it's a pretty highly parallel system. And this is another view of the time step that we showed earlier. I'll skip over that for now. Here's a quick summary of the speedups that we get in different parts compared. This is relative to GROMACS. And you'll notice that the range-limited non-bonded forces get a 50,000x speed up. Pretty remarkable. That's the part that I said, well, if we made this be 0, we'd still only have 4x. So it's pretty close to making it 0. We can speed up those computations almost arbitrarily because they're embarrassingly parallel. But we have all these other parts that we had to do work to speed up. And we were kind of blazing new territory because no one else has tried to accelerate these things to our knowledge in the past. So This is a little bit different view of the time step. This is actually a timing diagram of how the different pieces happen in order. And I don't think I have time to go through this in detail, but I'll be happy to talk to anyone over dinner who's interested in walking through the details of it. Anyway, overall, this leads to a performance on most common benchmark system, which is a protein called DHFR, or dihydrofolate reductase, 23,000 atoms approximately, that we can run time steps of 2.5 femtoseconds of simulation time in this program. And so we can do about 14,000 simulated nanoseconds per day, which is pretty good pace. The fastest general computer around can do something like 400, as far as I know, is the current record. And we're doing about 100x better than 5 years of Moore's Law compared to where we started, so we think that's pretty good too. A bit on power. So, as I said, we may be green, but we certainly do use a lot of power. A 512 node system, including its cooling, needs about 116 kilowatts of power. That doesn't sound so good. But here's a comparison of how much work we get done on that system. So we do about 0.2 kilowatt hours per nanosecond of simulated time. Our Desmond software package running on 512 x86 Core 2 Duo cores gets about 44 kilowatts per nanosecond of simulated time, and Blue Gene gets about 40 kilowatt hours per nanosecond of simulated time. So the specialization really helps because you're not wasting any power on doing any of the things a general purpose processor needs to do to keep the instruction stream flowing. So, quick conclusions. So, in order to really get this kind of speed up, you need to worry about keeping everything balanced properly and specialized and smoothly balanced. You've got to worry about Amdahl's law because at every step of the way, anything you do that makes something else faster will just make a new bottleneck appear. We can with Anton do millisecond cell simulations, and such a design is really very power efficient, but at the same time it's pretty hard to actually do this. It's a lot of work. Quick picture of the Anton ASIC and the Anton PC board. Chip statistics, I'm not going to go through these. We're out of time, and you can feel free to look at them. It's a 17 by 17 millimeter 90 nanometer ASIC clocking at 400 megahertz with the HTIS clocking at 800, and it's now operating in our labs. We have a 64 node system running. We should have a 512 node system running within the next month or so, and we are actually able to run some simulations on it. I had a little movie to show you, but unfortunately we're having some technical difficulties and it won't display. So what it was a picture of a protein called GB3, which essentially it's part of the human immune system. Nobody knows what it actually does, if it does anything. It seems to just sit there, but it's been extremely well studied and characterized, which is why we're interested in it. We know exactly what it's supposed to look like and act like, and we have NMR data that shows what it's supposed to look like and act like. And we've actually on our hardware simulated it and gotten a picture that overlays nearly perfectly on the NMR picture that we've got of it. So that, for us at least, is pretty exciting. So that's it. Thank you. Questions? No? I guess, okay, on to dinner then.
You blew them all away. So I'd like to thank you, Marty. Great talk, really enjoyed it. And I'd like to say dinner is served outside, same place where we had lunch. We'll take about a break for about an hour. We'll call it, meet here again at 10 to 7, and then we'll have a great panel. Ready, aim, fire, 20 years of hits and misses. We have actually panelists, or critiques, shall we call them critiques, giving you the ratings of what happened in the last 20 years, and it should be fun.